Hey there, we are going to be talking about identifying the oxidized and reduced substances within a redox reaction, as well as the oxidizing agents and reducing agents. Recall that anything that's oxidized is also the reducing agent, and anything that's reduced is called the oxidizing agent as well. So these are going to be questions from your worksheet. So you might recognize them. That's okay. In fact, that's intentional because we want to make sure that you're really also understanding the homework as well as just understanding the general concepts. So let's get started. I'm going to use red for oxidizing. So let's take a look. I noticed that copper is +2 and on the left, and copper is +1 on the right. And that means the charge is going down. How does a charge go down? How do you get more negative or less positive, rather? Either one. You would have to gain something that is negative, an electron. And so when I'm gaining electrons, that's reduction. So I'm going to change this color. I'm going to call this reduction. And this, by the way, is the oxidizing agent. Now, that means that aluminum has to be the substance being oxidized, but let's double check. Aluminum's charge is not written, or oxidation number is not written. It's 0 because it's a element by itself and the charge is not given, so the oxidation number is 0. Over here, aluminum is +3, so it goes from 0 to +3. How do you become more positive? Well, what would you do with your electrons? Would you gain more electrons or lose more electrons? If you're getting more positive, that's most likely you losing electrons, and that's oxidation. We also call this aluminum the reducing agent because it's helping copper to be reduced by giving it its electrons. Next one. 2LiCl plus F2 yields Cl2 plus 2LiF. So the first thing I want to do is look through and see if there's anything that's obvious. And right away I see that fluorine is by itself and chlorine's by itself. The rule is that those are 0 charges because they're by themselves and no charge was given to you, so you can assume that is a 0 charge. The next ones might be a little more tricky, as lithium, chlorine, and then over here, LiF. That I should be lowercase, by the way. So going back over to the common ions chart, if you haven't looked at your common ions chart, then you should. Common ions chart is here. Lithium is a +1 ion, and chlorine is a -1 ion, and fluorine is also a -1 ion. And if you don't have that on your common ions chart because you're doing the honors option, this is in group 1 lithium, so it's +1, and chlorine and fluorine are in group 17. That's -1. So we're going to write this in now. So lithium is +1, chlorine is -1. Lithium is +1, chlorine is -1. Okay, now we're going to label this. We have oxidation and reduction here. So what's being oxidized? What's being reduced? Well, I noticed that lithium goes from +1 to, +1. It's not being reduced or oxidized. And so we don't have to worry about it. We don't have to write anything about lithium. It's just not, something we need to consider. We're only looking for things that are being reduced or oxidized. So let's look for the thing that's being oxidized. I'm looking for something that oil rig, oxidation is losing electrons. So if you're losing electrons, you're becoming more positive. So what's becoming more positive? My chlorine goes from a -1 to a 0. Okay, so that is oxidation. Again, that also means that it's the reducing agent. It's the reducing agent because it gives electrons to the substance that's being reduced. Conversely, we see fluorine is 0 on the left and now -1 on the right. And so this is being reduced. And it's called the oxidizing agent. Remember, they're opposite. So if it's being reduced, that means it's the oxidizing agent. And it's the oxidizing agent because it is taking the electrons from the oxidized substance, in this case, the chlorine. Next question. Move this down just a little bit because I know we're going to need a little bit more room for this one. So I have to figure out my charges first. So I'm going to start with that. I'm going to look at the obvious ones. Are there any obvious ones in this question? Definitely. Oxygen here, while it has a 3 coefficient and a 2 subscript, that doesn't change anything. It's still by itself, so it's going to have 0 charge. Let's take a look at the first one, because now I don't see any sort of obvious ones. Take a look at the first one. This is actually from our previous video on oxidation numbers, but hydrogen and chlorine are there. I don't know anything about, carbon, not chlorine. Don't know anything about carbon because if I look here, it's in group 14. We don't have any rules for group 14. And also, if I look at my common ions chart, it's not there either. So we have to figure it out. And the way that we figure it out is by first figuring out what's hydrogen. Hydrogen is in the first group, and it's on your common ions chart, and it's +1. Now, we have to remember that these ionic compounds are neutral compounds. In other words, the negative and positive substances within this molecule have to add up to 0. So hydrogen is +1, but there are 4 of them. So that means total, it's going to be +4 from the hydrogens. So that means that the carbons are going to have to be -4 total, which makes each individual carbon, there's 2 of them, has to be -2. Let's go over to the other side. Oxygen and carbon. Again, we don't know carbon. We can't assume that it's -2 just because it's -2 on the left-hand side. It could be oxidized or reduced, in which case that would change the charge. So we have to look at what's the thing that is obvious that doesn't change. So if it's on the common ions chart, right, that's what we use. So let's take a look at the common ions chart for oxygen. Oxygen is on there. It's in -2 column. So it's a -2 charge, -2. And this is, again, a neutral compound. So total, this is going to add up to -4. And so that makes carbon +4. And there's only one of them. So that's going to be the charge for carbon. Now, I'll just write this here just so we keep it a little bit on the same line. If we have now hydrogens and carbons, which we know hydrogens are +1, hydrogens and oxygens. Oxygen is -2. We know that, again, this is going to equal 0. So 2 hydrogens, each one is +1, so that's +2. There's only one oxygen, and it happens to be -2, so that works out. So we're all good. So remember, we don't care about the big total for each of the molecules. We just care about what are the charges or the oxidation numbers rather for each of the elements. So let's take a look. What changes, what doesn't change? First off, I notice that hydrogen doesn't change. +1, +1 doesn't change. So let's take a look at carbon. Carbon goes from -2 to +4. How does something get more positive? You get more positive if you're talking about electrons by losing them. And so this is going to be loss of electrons, L, oil rig, right? Oxidation is losing, it's oxidation. Again, it's also called the reducing agent, or RED agent, okay? Next, we'll do the oxygen, and I'm going to pull this out here. And oxygen is in both places, and that's okay. Oxygen goes from 0 to a -2 in both cases. So this is going to be reduced because it obviously gained electrons. This is also called the oxidation agent. Next, let's take a look at this one. Potassium is, and I'm going to go a little bit faster on this one, but I'll explain what I'm doing. Potassium is a +1, and then this is a polyatomic ion, oxygen and hydrogen. I know that because if you look at your common ions chart, you'll see oxygen and hydrogen hydroxide. That's a -1. Always check if there are 3 elements in the molecules. As you can see, most of them, all of them have it, in this case 3. You want to check to see that if 2 of those elements are in a polyatomic ion. If they are, you're looking for that one charge for the polyatomic ion. So nickel is an interesting one. I know it's not on the common ions chart, but I do know that sulfate, SO4, is on there. It's a -2 charge. So that means that nickel has to be a +2. Again, potassium is a +1, but there's 2 of them. That's going to be a +2. And sulfate is a -2, and that makes sense. There's only one of them, so it's just -2. That adds up to 0. And then lastly, we have OH, right? Hydroxide. This is going to be a -1, but there are 2 of them. See the 2 outside of the parentheses, so that's -2. And then that makes the nickel +2. So what is something interesting that we note? If I look at potassium, +1, +1, hydroxide, -1, -1, nickel, nickel, +2, +2, and then sulfate, -2, -2. All of these are the exact same on the left and right. What do we say about this one? This one is not a redox reaction. Okay? Some reactions are going to be like that, where they're not a redox. All right. And we're going to do this last one here to finish it out. And again, I kind of remember the common ions chart. I don't expect anyone to memorize it, but you want to look at your common ions chart for what I'm doing here. But sodium is a +1 charge. It's in the first group. And there are 2 of them, so it's +2 total. Sulfate is a -2 charge by itself. There's only one, so one sulfate, so it's -2. That makes sense because +2 -2 makes 0. With hydrochloric acid, this would be +1 for the hydrogen, -1 for chlorine. that makes sense. It's, again, 0. Notice, by the way, I didn't do anything about the coefficients. The coefficients don't change the charges because they impact both of the elements in the molecule. So it doesn't impact it because it impacts it the same way for both of the elements. So we don't need to factor that in. It's not something we have to, add as an extra step. So Na is a +1, Cl is a -1, hydrogens are +1, but there are 2 of them, so it's +2. Sulfate is a -2, there's only 1 of them. And this is again an example of something that is not a redox. Okay? I hope that was helpful. Take care.